Okie dokie. Um, so pretty much everyone who responded to the Google form seemed to understand these formulas, and that's kind of expected. They're not terribly difficult. The only thing that's annoying about them is I guess, the length of them. But I want to always go over the exit tickets that I assigned, so we have a little bit of feedback as we kind of navigate these couple of weeks here. So the sine 255, there's a lot of different angle combinations you could have used. Any one of these three obviously add up to 255. There's several that you could have done a subtraction of two angles. You could have done 300 minus 45. They'll all eventually simplify to an equivalent answer. The work just in between those steps is going to always look a little bit different. So I chose to just model one of them because it's a little bit redundant. The last one, when you use 225 plus 30, submitting it into your formula or substituting into your formula, evaluate each from the unit circle, and simplify and combine. You have negative rad 6 minus rad 2 all over 4. All right. The only thing that would have been different if you used a different pairing would be maybe you have a different combo, or excuse me, a different order of terms, but it would all be equivalent. Okay. So today we're just going to kind of finish up this section 10.1 on your sine and cosine formulas. There's not a whole lot that we use them for, so you'll see between yesterday's video and today all the types of problems that they're good for. So here is a problem. Oh, here comes my dog. You guys were looking forward to that. Ollie, what do you see? There's some deer going in the backyard, so he's barking at them. So here we see an example of some information. I forgot parentheses around that. Some angles that are given to us, but clearly based on the ratios that they're identified, these are definitely not common angles anywhere on the unit circle. There's nowhere on the unit circle in the standard 20 angles that are listed that has a 4/5. Obviously, there's still positions there, but we have some information about alpha, some information about beta. We don't know what those exact values are. We know alpha is in quadrant 1, beta is in quadrant 2, and we know the corresponding sine ratios for them. We want to know what sine of alpha minus beta is, which alpha minus beta is an altogether different angle. So here's the deal. I don't want you touching a calculator for this problem. We could use sine inverse and get rounded answers, but this is all about giving exact values here. So I'm going to even add that there. So let's just start with our formula. Sine alpha minus beta, we know, is sine alpha cosine beta minus cosine alpha sine beta. And we know two of these because they gave us the sine value. Sine alpha is 4/5. We don't know cosine beta, so I'm going to leave a little placeholder there. We don't know cosine alpha, and they gave us 12/13 as sine beta. So the challenge here, and it's not much of a challenge, is just setting up a useful little triangle for both alpha and beta and figuring out what those cosine ratios are. So I chose nice numbers here. You guys know me by now. They're not always going to be nice values that work out well. But for instance, if sine of alpha is 4/5, alpha is in quadrant 1. So there's alpha. We know 4, 5, obviously this is going to be side 3. And using this triangle, we can find cosine alpha is now 3/5. Similarly, for cosine beta, well, I know beta is in quadrant 2. I know sine of beta is 12/13. So I can set up a different triangle now for beta into quadrant 2. We know sine is 12/13 for beta. The third leg, it's a 5, 12, 13 triangle. However, being in quadrant 2, it's going to be -5 for that side length, which means my ratio for cosine beta is negative 5 over 13. At this point, we have everything we need. We can just simplify. Negative 20 over 65 minus 36 over 65. And we have my ratio. Keep in mind, I don't know what alpha's measurement is, I don't know what beta's measurement is, and I don't know the difference of that angle's measurement is, but now I know part of the ratio for it. You would set this up very similarly for any of the other formulas that's being asked of you. Now, let's kind of talk about another task, and this is a little bit of chapter 8 that we kind of cut out because of the school closing. However, I think it's still pretty straightforward and fair to kind of discuss remotely here. So the task is, here's two very different looking, very complicated looking expressions that, as messy as they look, they're going to simplify or whittle down to quite a bit, down to a single trig function. Okay, so I'm just organizing my notes off screen here. What your goal here is to make substitutions, to identify patterns, basically just to apply simple algebra until all of this reduces down to just one trig function, no other pieces. Okay, so I'm going to first kind of focus on my numerator, because right away, both of those expressions, the sum and the difference, have formulas. So it's going to temporarily look a lot worse before it gets better, because sine A plus B and sine A minus B, both of those are going to make a more expanded version. So sine alpha plus beta, that's sine alpha cosine beta plus cosine alpha sine beta. Sine alpha minus beta, which we're adding, is now sine alpha cosine beta minus cosine alpha sine beta. Just copying down those denominators. Now, take a look at a couple terms. You're going to notice real quick, we have a cosine alpha sine beta, cosine alpha sine beta. One's positive, one's negative, so these two terms cancel. Sine alpha cosine beta, another sine alpha cosine beta. Those two things are like terms and they can combine to 2 sine alpha cosine beta. Bringing over the denominator, you're going to see very quickly cosine beta also cancel, and we're left with 2 sine alpha over cosine alpha, and most of you probably already know what's next. But sine over cosine, that is tan, or tangent alpha. And we simplified it. Single trig function, doesn't matter that there's a coefficient, it just matters that there's one trig function. Now, let's talk about this other one that's kind of squished off to the side here. Cosine x times cosine y times the quantity tan x plus tan y. So first thing I'm going to do is I'm going to kind of separate all of that. I'm going to distribute the cosines to both tangents. So we're going to have, and I'm going to try and write as small as I can with a Sharpie here, cosine x cosine y tan x plus cosine x cosine y tan y. Okay, now I'm going to go down to where I have a little bit more space here. So cosine x cosine y I'm going to leave alone. Tan x, just like we just saw down here, tan can be rewritten as sines and cosines, and I'm going to do that because you're going to notice very quickly some things cancel out very nicely. So cosine x cosine y times tangent of x is sine of x over cosine y plus cosine x cosine y. Tangent of y is now sine y over cosine y. Cosine y cancels, and oops, this would have been a cosine x. Shouldn't have canceled in both. So cosine x cancels in the first term. Cosines y cancel in the second term. And let's just kind of rewrite what's left. So we have a cosine y sine x plus cosine x sine y. Now, it might not be the most recognizable in this form because the order of the terms don't really match, but we know multiplication. I can move these terms around and it doesn't really affect the answer. So just to make it more obvious, I'm going to switch these two terms around. I'm going to leave these terms alone, and this entire expression is an identity that we just discussed yesterday. Sine of the first, cosine of the second, plus cosine of the first, sine of the second. That is your sine addition formula. And the two angles we're adding are x and y. So this is my single trig term. Doesn't matter that there's multiple pieces inside. I only wanted one trig term. And that would be the simplified final answer. So today's Google form is going to have an exit ticket asking you to find some type of expression simplified down here. Email me or chat me if you have any questions on it.